All right, so we're going to start with number 12. And then what, 17 was it? I think that was it. So number 12, we have a swimmer in still water at a speed of this. He aims so he can swim directly across a river that has a downstream current of this. So this one, I'm probably going to include a diagram in it, but I can put that. I'll probably put that in my y. So it's going to be just the generic form of the y here. So let's see, this is 12, and we'll say the swimmer moves relative to both the water and the bank. Because that's really what this problem's all about. It's about relative motion. You know, we know his motion relative to one thing. How does it make his motion relative to something else? So with these, there's some key phrases to understand. I might actually add in here the motion, and by motion I mean velocity, depends on frame of reference. That's the big overarching concept here is, you know, if you're in the frame of reference of the bank, you're going to see the swimmer moving at one speed and in a certain direction. But if you're the water, you're going to see him move at a different speed and in a different direction completely. All right. So, and I'll put my little diagram up here. So they tell me. So some key understandings here, just to kind of pull out of this question. When they say something like still water, what they're telling you is the speed of the swimmer compared to the water. So that would be, they're telling me the speed in the reference frame of the water by that turn of phrase, still water. Then if I look at how they stated the question, he aims so he can swim directly across a river. So his final velocity with respect to the bank is going to be directly across. Does that mean he points himself directly across? No, he's got to point himself upstream, and then his final velocity with respect to the bank will end up directly across. And then they tell me the downstream current, which would be the speed of the water relative to the bank. All right, so my diagram here. The current is going to go that way, so that I'm going to label as the velocity of the water with respect to the bank. The swimmer wants to end up going this way, so that's the velocity of the swimmer with respect to the bank. To accomplish that, he's going to have to point himself in this direction, because that will be the velocity of the swimmer with respect to the water.
So the B's, sorry, just for clarification, the B's are also in subscript?
Yep. So that's kind of the idea of this one, you know, a diagram would be helpful. Not necessary, or you could put it as part of your how, but I think it's useful. All right? So, physics-wise, I would go up to my equation sheet, and I'd find that we have an equation. I think it's written this way: velocity of AB plus velocity of BC equals velocity of AC. It might be different subscripts, but I think that's what's on our equation sheet. I'm too lazy to pull up our equation sheet right now. And so that's my problem. I'm going to just keep in mind that it's in 2 dimensions. So that's my velocity. Rather than AB, I have swimmer to water. I add to that the velocity of the water to the bank. And I might have swapped colors, sorry folks. And I get the velocity of the swimmer to the bank. So, and I think I did. So remember with this equation, the middle two subscripts have to agree, and then your final outcome is the outer two subscripts, is the way to think of ordering it. And geometrically, that's how it goes together. I have a nice right angle here, even though my drawing doesn't look like it. Right? And let's see what they want to know. They want to know the swimmer's direction, upstream from straight across. So the angle that's upstream from straight across would be this angle theta here. So that'll be good to find. They also want to know how much time does the swimmer spend getting across the 403-meter river. Ooh, I better add something to my y to do part B, because there's a crucial understanding here. Maybe we'll put it in red. And the crucial understanding is that the velocity and the displacement must be in the same direction. That's crucial to understand. Okay? And it seems like something, oh, that makes sense. If you're moving this way, your displacement's going to be that way. It seems like a very trivial fact, but it becomes important. Okay? So that's my velocity triangle. I would have an identical displacement triangle. So that would be the displacement of the swimmer with the water. That would be the displacement of the water to the bank. And that would be the displacement of the swimmer to the bank. So just a similar triangle. In fact, the scaling factor between them is time. Right? Because we also remember from our equation sheet that D equals D naught plus V delta T. So now let's put some numbers with it, unless there's questions. So I want to figure out theta. Let's see what they tell me. Do they tell me VS? Yes. VSW is 6.616 for me. So VSW is 6.16 meters per second. And 3.54 is VWB, 3.54. All right, opposite and the hypotenuse. Oh, that's a sine function, isn't it? Opposite and hypotenuse. So I can do sine of theta equals opposite, which is 3.54 meters per second, over hypotenuse, which is 6.16 meters per second. Oh, good. The units are going to cancel out. And then I can find what my theta is. Make sure your calculator is in degrees. I got 35.1 degrees, which makes sense to me. I would like to know what VSB is, because they tell me, oh, that's the other, they tell me that this is what, 403? 403? But I know the angle that triangle's at, but I don't know anything else about it, right? So I want to use the fact that displacement is related to velocity and time to find the time. If I have that displacement, I need the velocity that's in that direction. Or I can say, oh, wait a minute, couldn't I figure out this displacement? Because these are similar triangles, right? So this angle is also theta. So could I figure out the red displacement? Yeah. Could I figure out the blue displacement? No, with the green displacement.
Oh, blue, yeah.
Yeah.
Also, you can get the red displacement.
Actually, I would have to use cosine to find the red displacement.
Okay.
Because I know two angles and a side, not two sides.
But once you figured out the second side, you could figure out the third.
Right, right.
Yeah.
Because remember, triangles have 6 things. As soon as I know 3 of them, I can find the other 3. As long as one thing is an angle and one thing's a side. Then I'm home free. So I know the green displacement, 403 meters. I don't know the green velocity, but I could find it. I don't know the red displacement, but I know I could find it, and then I could use the red velocity, which I know. Or, since I know the blue velocity, I could find the blue displacement, and then use the blue velocity to find the time. What's your preference? Which one do you look at and go, oh, that makes sense? To use, I'll recap. To use green, or to use red, or to use blue? You want to use red? Okay. So we're going to do it using red, but realize we can do it with any of them. So with red, I know my velocity, but I need to know my displacement. So I'm going to find my displacement from the fact that I know theta and I know the green side of the displacement triangle. So I'm going to use that cosine of theta would equal adjacent 403 meters over DSW. So cosine of 35.1 degrees equals 403 meters over DSW. So DSW equals. Now, just for intuitiveness, do I expect a number bigger or smaller than 403? Bigger. So if I don't get a number bigger than 403, check your math. No, it's good to realize that, though, right? Because then you can say, oh, wait a minute, I got 492. Oh, that makes sense. Or I got 200. Or maybe I screwed something up, you know? But, so I'm expecting a bigger number, and I got it. So That's 492.575 meters. Now I can use this equation and say I go 492.57 meters. I'm going to call where I started 0. I did that at 6.16 meters per second, and I want to find time. And I get 79, actually I get 80.0, even rounding, seconds. All right, so 17. We have a momentum one here, right? Two cars approach the intersection. We got a red one traveling east and a blue one traveling north. They collide and stick together. So what type of collision? Inelastic, totally inelastic, right? So I'd probably start off here. This is 17. Probably start off with mom is conserved, just to make sure that completely understand that. So beforehand, we have the momentum of the red going east, and the momentum of the blue going north, right? And then crash. See. Inelastic. I could draw like impulses and everything there, but for this problem it's not going to be crucial. Afterwards, which direction do you, just intuitively, which direction do you think they're going to head? Northeast-ish, right? Yeah. I'm going to draw that in green because that's a new thing called RB, because that's red and blue coming together. I wish I had purple. I should have changed my green to purple, but all right, because those the two objects coming together. So that's what you would need for your Y: before, during, and after. And I'm going to redraw that here for my how, because I want to keep in mind that I have these two dimensions. Except I'm going to draw it better vectorially now, because I know for momentum to be conserved, the momentum before added all up equals the momentum afterwards, right? Oh, I got two momentums before and one after. What type of figure is that going to make? Three sides, a triangle. So I've got momentum of the red plus the momentum of the blue equals the momentum of our new object, red-blue. And for my equation sheet, I remember that momentum is inertia times velocity. Let's see what they want to know. What is the speed of the combined cars after collision? So they want to know the length of that green side. What direction does the combined cars move after the collision? And they want that in terms of north of east. So looking at my diagram, north of east, that angle would be theta right here. So I want the magnitude of the green and then the angle theta. I know momentum of the red because I know its mass and I know its speed, right? So I know the magnitude of that, and I have its direction. Do I know the magnitude? Do I know the momentum of B? Do I know its mass? Do I know its velocity, i.e. its speed and direction? Yeah. So I know these two sides of my right triangle. How can I find the third side, the hypotenuse side? I can use Pythagoras, right? Probably. So I'm going to find out the speed, which is the magnitude of that side, by doing Pythagoras. PR squared plus PB squared equals PRB squared. And here I can do the mass R, speed of R squared plus speed of B squared equals. Now, what's going to be the mass of these two things stuck together? Their masses added together. So we have the mass of the red plus the mass of the blue times the speed of the red-blue. That whole thing squared. Now, however tempting it is, you cannot just take a square root of all the things because they're added, right? That could be a math. But you know everything here. You know the mass of the red, you know the speed of the red, you know the mass of the blue, you know the speed of the blue, you know the mass of the red, you know the mass of the blue. Oh, good, we have one thing we don't know. Otherwise, why bother? So you solve all this, and you come up with the speed of this new red-blue object. And that's in meters per second. Yeah, I'm rushing a little bit because our time is running short. You guys can do that, right? So now, how are we going to find theta? If we know the red and blue sides, how are those related to theta? How is an opposite and an adjacent side related to the angle? Tangent, yep. So I can do that the tan of theta equals the opposite, which is momentum of the blue, over momentum of the red. So theta is the inverse tan. Do you guys call it inverse tan or arctan? Inverse? I can never remember what math I should do. MB, speed of B,